No worries. That's not that bad.
So I start and then you go for the first slide. I'll just introduce.
Oh, you start. Oh, okay, perfect. But maybe 10, 5 more minutes. We're gonna wait 5 more minutes, and then we'll start. Hope you know. Sorry, that was me. Sorry. Sorry, yeah, that's a dramatic feel.
Yeah. What we like to find because we just
Come on. You look like 7 and 10 now? I'm surprised.
why? No, I don't need that much.
Sorry?
Yeah, I think so.
All right. Oh, wow. Okay. I'm going to talk softly. Thank you for coming, especially at an 8 a.m. tutorial on the first day of ICAPS. So obviously you guys are really, really excited to learn what we're going to talk about today, Go Recognition Design. So Sarah and I are going to be presenters, and she's going to start off essentially with the tutorial with the first two parts, and I'll end up with the second, slightly on the second part. And we like it to be interactive. We also have a game there that Sarah created quite a while back to, essentially you need to catch mice, right? Please ask questions if you have any. The more questions you ask, the more I think that you will get out of the tutorial. And if you don't ask questions, I guess we might end early. Which is probably a bad thing to say. Maybe we're if you don't ask questions, we're going to keep you here an hour later, right? That's the goal.
Yeah.
Okay, so without further ado, Sarah's going to start.
Thank you. Hi. So what do we want to achieve today? As William said, we're here to present goal recognition design in its various forms and the work that we've been doing for, Christabel just mentioned, for the past 5 years. So we're going to present the goal recognition design framework, which I'm going to call GRD for short. Hope that works for you guys. Then we are going to, throughout the presentation, we're going to use one running example, but we are going to try and link and map GRD to various real-world applications. We want to show you specifically for ICAPS audience, we want to show you the relationship that we have between GRD and planning, specifically because we are planning, our background is planning, so there is a strong connection in the tools that we use and the approaches that we kind of adopt for GRD. And we are going to finish up by specifying open challenges, things that we think are worth investigating. As William said, that there is the Go Recognition Design game here, the GRD game, that I didn't develop it, a student of mine did. And to give you a feeling of what GRD is and why it is valuable. So please feel free to use the laptop here now or during the break, whenever you feel like. And I also wanted to mention that the slides are on that website over there if you want to follow with the slides online. So hopefully you can read. Let us know if you can't, if you have trouble linking to the PDF of the tutorial. So yeah, I have to remember that I have the screen here. So a little bit about us. I am now a postdoc at the Harvard School of Engineering and Applied Sciences. I'm kind of working on a generalization of Go Recognition Design to what I call utility maximizing design, but I'm very interested in applying GRD to various settings, and specifically I am now working on thinking of how GRD works for human-robot collaborations. GRD was the topic of my PhD thesis at the Technion, and we included here our contact details. If you guys are interested in finding out more, have any questions, please feel free to contact us. How about you?
Right. And I'm William. I'm currently an assistant professor at WashU in St. Louis. My background is not really in GRD, and the reason is because GRD didn't exist until 5 years ago, and Sarah talked about it, ICAPS 2014, I think. And so when I heard Sarah's presentation, ICAPS, and I talked to her at the poster, it got me really, really excited. And excited enough that I sent Christabel, who was a master's student of mine at the time, a paper exactly 5 years ago today. She just reminded me, right? And I started working on that. And my primary research area is mostly in distributed application, distributed systems, multi-agent systems, with some planning under uncertainty background. So when I heard about Sarah, then I thought, we could have stochastic applications as well, and that's how I got into GRD. Right?
Great. So let's start. Some of you I know, and I know that you guys know what goal recognition and goal recognition design is, but we wanted to keep it as basic as possible to give you a feeling of what it is that we're doing here. So let's start by understanding what the essence of goal recognition is. What is the task that we're interested in here? So think of this very simple example of an airport where you have an entry point and users, and we here in ICAPS I can feel comfortable saying agents, enter the system from one initial state, and we know that agents may aim either at the left door or the right door. Now we can make some additional simplifying assumptions just for the sake of the discussion. We know that the agents, let's say for now, that the agents are optimal, actions are deterministic, the system is fully observable both for an observer but also for the agents, and movement is perpendicular, right? We can only move in the cardinal directions. What would be recognition in this case? Recognition will involve observing a specific behavior. For example, we see this agent walking into the room or the terminal, whatever, walking in, going right, and then going up. According to the assumptions that we make about how agents behave, we know that we can recognize the goal of this agent as being the goal number 2 on the right. Okay, so this process of mapping behaviors to goals is what we call goal recognition. And this is a well-established field. I recently learned that right from the start when they defined AI, they actually appreciated the value of goal recognition as a very important task, because when we interact, we want to know what agents are trying to achieve by observing their behavior. So this is goal recognition. Goal recognition design, which as William said was my PhD topic, is basically trying to think of ways to design environments in order to facilitate the goal recognition task. So we take this airport, for example, and we try to analyze the setting in which agents act, and try to understand what it is about the environment that makes goal recognition easy or hard. So the first thing that we needed to do is define a measure. How do we measure an environment? And in our case, we decided to go for a worst case analysis and try to understand what is the maximum number of steps an agent can take in an environment before we understand what the goal of the agent is. We call this measure worst case distinctiveness, and in this case, we see that the agent that is circled she can actually walk all the way up to the wall before she will turn left or right. Again, under the assumptions that we made, the assumptions here are very important. We assume that the agents are optimal. The agents have multiple ways to achieve their goal, but in the worst case, they will walk all the way up to the wall before revealing their goal to an observer. That's stage number 1. That's a measure. This is the measure that we want to minimize in this case. We want to optimize this environment by minimizing the worst case distinctiveness. Let's say that we have a way to modify the environment, and it's often the case where we can change environments in order to support some utility function. So in this case, we would want to minimize the worst case distinctiveness, for example, by setting up barriers. Okay, in an airport, it's very common to have barriers set up. You can also actually build the airport in a way that supports recognition. So let's see one solution that will achieve a maximal or minimize the worst case distinctiveness. In this, if we block all the actions marked by this red wall, we will achieve perfect recognition, right? The first step will achieve, reveal the agent's goal. But if we translate this to the real-world application that we have here, this translates into an unusable environment, right? We don't want to walk into the airport and follow a corridor that leads us to our path, right? That's not something that we want. So what we are trying to do in GRD is to think about the minimal change that is needed to achieve the minimal worst-case distinctiveness that is possible. And in this case, our techniques, well, where is the solution? Sorry for that. Something messed up. Sorry for that. So the really big punchline of this slide is that now I show you that if we block this action, we are actually achieving the same results, so WCD of 0, without the need to actually build the wall. So I'll show you this example later on, after the break, so you guys see this beautiful fountain that is built in the entrance of the room that actually makes recognition possible after one step. So goal recognition is an online task. We are analyzing behaviors of agents and trying to map them to goals. Worst case distinctiveness is an approach that takes an offline design approach and tries to understand how to change an environment in order to minimize the worst case distinctiveness. Now, you guys are planning people, so I have this comment here just to kind of appeal to other people that research other forms of AI, but if you think of goal recognition, it is very similar to inverse reinforcement learning, right? And what we are doing here is basically doing design for plan recognition, but we could also do design for reinforcement learning, etc., inverse reinforcement learning. But the idea here is that we are doing design in order to understand what our agents are trying to achieve and how they operate. So in terms of applications, that's actually, I find this to be the easy part, because there's so many applications where goal recognition is relevant to, and in many of these cases it is possible to actually access the environment and change it. Instead of working hard on analyzing behaviors that don't reveal the goal, there are many ways in which we can change the system, and this is what I'm interested in understanding. So for example, we showed you the intrusion detection example where we have an environment that we can manipulate by creating physical changes to the environment. But this is not only a physical set, and this does not apply to only specific settings, right? This is a general framework. We are planning people, so this is a general framework that could support any goal recognition setting where our agents are modeled as planning agents. So this, for example, is a smart home setting. We're trying to think about ways to redistribute furniture in an environment where we're trying to recognize the goals of, for example, a user with some disability. So we can think of ways to actually move the couch in a way that reveals when an agent is approaching a hot oven. But the same ideas apply to virtual environments where we're trying to use GRD to understand what consumers are trying to buy on a website. Or, as I said, my personal focus at the moment, understanding how we can design environments for more effective human-robot collaboration. I'm saying human-robot. I am now in the robot-robot communication stage. Humans are, to me, a bit too difficult at the moment, but I'm trying to think about, when you think of human-robot collaboration, you think about where would goal recognition be essential. So what I recently realized is that it goes in both ways, right? On the one hand, we want to make sure that the robot that is helping this user understands its intention as early as possible, right? So it can assist it in an effective way. But it also goes the other way. The same applies to us humans that are it's very important that we understand what robots are trying to achieve when they're interacting with us, so we don't feel intimidated and the collaboration is effective.
Is it okay to ask?
Yeah, please do.
Yeah, the question is the goals you are mentioning about, is that predefined goals?
Yes, yes.
So if you have, a few goals, for example, right, it may be easier to define, to recognize if you have, hundreds of goals and similar settings. Would that be harder? And are you going to address that kind of problem?
So you're talking about a specific setting where we have multiple goals, or we have similar? Oh, yeah. So in the
similar settings.
Oh, wait, so that's, I see this as two questions, so that's great. So one question is, do we support multiple goals? Of course we do. We can do a worst case analysis over all goals, or alternatively, maybe there is one goal that you care about and all the rest are, you just want to kind of make sure that you distinguish one of the goals. That's also supported by the framework, but this really depends on the application. Right? The worst case distinctiveness can be whether people are approaching the Mona Lisa or not, right? Something like that. The second question is, do these techniques generalize over environments? So this is, basically we are assuming that we have a model of a given environment. The tools are general in that they can be supported, transformed from model to model, but the analysis is model specific. So it's a model-based analysis. Hope I answered the question, and please answer questions. This makes it fun for.
So the whole day you are going to cover those kind of topics?
Yes. So yeah, I'm going to actually cover the outline right now. So the outline is going to be elements. So first I'm going to describe what are the elements, what is the recipe that we need to follow in order to define a goal recognition design problem. What are the characteristics of a goal recognition and a goal recognition design problem. Then I'm going to cover the work that I've done on GRD in deterministic environments. So we're going to assume classical planning models. William is going to cover stochastic models, so GRD in stochastic environments. Then if we have time, we don't necessarily will have time for this. I'll talk about goal recognition design that supports agents with partial information. So throughout most of the tutorial, we're going to assume that agents are perfectly informed. I'm now working on a framework that it does not assume that, and then we will conclude. And again, the slides, if you want to follow, the slides are online on William's website. So what it is that we need to define, we need to define a goal recognition design problem. So of course, one of the elements of a goal recognition design problem is a goal recognition setting. The goal recognition setting defines an environment in which agents act. The acting agents, I call this an actor, but we differ in the term. So sometimes we'll say acting agent, sometimes we'll say actor, but this is the agent that produces change in the environment, and a recognition system. Well, now we call this recognition system to make it clear that we are not considering an active recognizer. But of course, when you generalize these models, and we'll talk about this in the conclusion, you can actually think of this as an interactive environment where we have two active agents that are trying to understand what each other's goals are. But we are here for today. We are going to assume that the recognizer is static and is observing the actor and trying to recognize its objectives. And then we are going to talk about the design model, right? What are the ways to introduce change to the environment? We are assuming that this is given as input. So what is the environment? So the environment that which is sometimes called the domain theory, is basically a state space. And we are using planning tools, so it's very easy for us to define the world using a set of features and set of actions that kind of change the world by performing actions with preconditioned actions. I'll actually talk more about this framework later on, but the thing to note, and what I wanted to kind of mention here, is that the general framework supports any kind of change and actions that can change in the environment. So the actions can be deterministic, non-deterministic, stochastic, etc. The idea is, and as was mentioned here, we have a set of predefined goals. We know what the possible goals are. Basically, the role of the environment component is to define the set of possible behaviors. How can agents behave in an environment? What are the possible trajectories that we would need to analyze for the goal recognition setting? The actor, and this is a subtle point here, the actor specifies the assumptions made by the recognizer about the actor. This is not necessarily the way the actor is behaving, but the actor component specifies the assumptions that are made by the observer about how an agent plans to achieve its goal. And for example, if I'm assuming that an agent is optimal, then that's the way I'm going to interpret its behavior. Okay? In all of our cases, we are assuming that the agent enters the environment and follows a specific goal. Right? It doesn't change, it doesn't reason. There is a lot of work on adapting goals. We are assuming that the agents have a premeditated goal and that they're following a plan to their goal. And again, today, I mentioned this before, we are going to discuss a single agent setting. This is sometimes confusing to people that are maybe mostly not from the planning community. It's a single agent. We are analyzing an environment where we have multiple agents, but our analysis is specific to a single agent that is acting and in order to achieve its goal. Yeah?
Do we assume the agent is following an optimal policy? Does the agent try to obfuscate intentionally?
Oh, great questions. We are going to show different models that play with these assumptions, that change them. In the example that I showed you, we were assuming that the agent is agnostic, but actually I have a slide coming up on that. It's actually a good point. So let's talk more about the actor. Right? When we define the recognition setting, and still I'm not talking about design, this is for any goal recognition setting, you need to think about the following questions. How does the actor make decisions? What does the actor know, right? What is it? Is it fully informed, has partial information? And as you mentioned, what is the actor's relationship to the recognizer? And again, I mean, of course, we can also ask the question of what is the best formalism to use. But so how does the actor make decisions? For example, we can assume that the actor is optimal. That's not necessarily always applicable, but we can assume that for simplicity in order to get some worst case results. Or we can now assume that the agent is suboptimal. I mean, this really depends on the applications and the complexity of the tools that we want to use. We can make various assumptions about what the actor knows. As I said, the actor can be fully informed, partially informed. In any case, it is important to understand what we are assuming about the actor. And this is a very important point, we need to understand what is the role that the actor is taking in the recognition process. So in general, we have a classification that divides these settings. Sorry, I'm doing something wrong, sorry. We have a classification that divides recognition setting generally to agnostic settings, where the agent is not aware of the recognition process, adversarial, when the agent is actually trying to obfuscate its objectives, and intended, where the agent is actually trying to help the recognizer understand its objectives. So we view this work as very strongly related to explainable planning, where we have a workshop. There is a workshop tomorrow that's going to dive into this topic. But the idea in explainable planning, usually we are representing the actor that is trying to produce behaviors that are legible, that are easy to interpret. Here today, we are representing the observer. We are trying to understand, given the assumptions that we make about the actor, how can we effectively make sure that the goal of the agent, of any agent, will be easy to recognize. And again, there are different formalisms to represent the actor. We are using domain theory from planning, following Ramirez and Geffner's work, but there are plan libraries and other various techniques to represent the actor. So finally, the final element of the goal recognition setting is the recognizer, right? We made assumption about the environment. We have the actor that kind of serves as an overlay in the environment. Among the possible behaviors, what are the actual behaviors that agents will follow to each goal? But then we have the notion of observability. Sometimes, even though we have perfect information, if the agent has perfect information and we know exactly what the agent is going to do, we still can't see the agent clearly, right? So in some settings, we have partial observability, and we need to account for that. So that's what we account for here in the recognizer recognition system process element of the model. The objective is also something that can vary. We may want to know what the plan of an agent is, what are the activities that are performed. But today we're going to focus on goal recognition. Goal recognition is about understanding what is the final state that an agent is trying to achieve. So this is our objective. We want to do design in order to understand what is the final state that agents are trying to achieve. And we are going to discuss work that has focused on that. Final element that we have in a goal recognition design model is the design model. And we are, again, not the only, our work is not exclusive in the sense that people have thought about changing behaviors, influencing behaviors via change. So the work that preceded goal recognition design was mostly about online interaction with agents. So basically, in some cases, you can just ask the agent what they're trying to achieve, or in more elaborate settings, think about the smart ways to provoke agents to interact in an effective way to understand what their goal is. But today, we are focusing on an offline analysis. What is the best way to facilitate goal recognition via design? So that was the intro. This was just to give you an idea of how we define a goal recognition design problem. If there are any questions, I'd be very happy to answer them now. If not, yes.
Is this the presentation available to us?
Here.
Okay.
This is the website. You can download it. You can view it online. Yeah. Yes. So the next stage is to actually go into the details of the work that we've done. So what I described so far is the general motivation, hopefully giving you some relevant applications for which goal recognition design is relevant. And now we want to dive into the technical details of how we did the actual work. So here's my fountain that was missing before. We took a goal recognition setting, we analyzed it for worst case behavior, and we found this beautiful fountain to construct in the entrance of the room to make sure that behavior of agent is easily recognized. How do we find this change in an effective way? So the outline for the rest of this, how much longer do I have? I think the coffee break. So it's the rest until our coffee break. What I'm going to do is briefly cover automated planning, assuming you guys are familiar with this stuff even better. Some of you even better than me. And then I'm going to give the problem definition. How do we define a goal recognition design problem for deterministic environment? I'm going to talk about computing worst-case distinctiveness using compilations to classical planning. And then I'm going to talk about the optimization stage. How do we find the best way to introduce change using specifically techniques for safe pruning. So yeah, hopefully. So background, domain-independent planning. So we're here in ICAPS, you all know this, but I'll cover it briefly again. We have an initial world state, we have a desired goal condition, and we have a set of deterministic actions that change the state of the world. Specifically, we use strips to represent this world, which means we have a set of Boolean propositions that are used to represent a world state, and the goal conditions are a subset of this set. each action is a triple with precondition add effects and delete effects. And the solution that we want to find in a planning problem is a sequence that minimizes the cost from the initial world state to the goal state. And it's optimal if it minimizes sum of action costs. Now, where do we use planning here? Why am I saying this? First, because we are assuming that our agents are modeled as planning agents. The actor is modeled as a planning actor. I'll show you that we'll use planning in a different way. We're actually going to use compilations to planning to actually solve our problem, but as a first stage, this is the way we model our agents. And of course, there are other models of planning. There are stochastic models, which William will cover. They're conformant, which conformant are for agents with no sensing. Contingent planning, which is I'm going to cover at the end of the tutorial if we have time. But there are different models for planning that we can use for GRD. So as I said, we are using a strict model where we have proposition, initial state, goal state, and actions. We have cost that can be assigned to each action. And we have action sequences, which are the sequences that the agents follow. Now, as you know, the task is when we define it, if we could define the state space explicitly, the problem is we could have used any search algorithm like Dijkstra to find a solution. But what we are actually interested are large domains where exploring the state space is useless. We want to find a path from an initial state to a goal state, and we are interested in domains where doing this really requires finding efficient techniques. So this whole conference is about that. But I want to focus on two techniques that are typically used for efficient planning. One of them is pruning. When we just cut off part of the search space, when we understand that it is not relevant for finding a solution. Specifically, I use technique for safe pruning. Safe pruning means that we guarantee that at least one optimal solution is not pruned when at least one desired solution is not pruned. That's what safe means. A heuristic function gives us a way to, and I don't know if you guys know, my master's advisor, Carmel Dumschlag, used to call it a sense of smell. So heuristic functions helps us prioritize which paths to follow to achieve our goal. And it is admissible when it underestimates the cost to goal. Of course, we want to have a way to effectively automatically extract heuristics from our problem description. And we want to balance how informative the heuristics are, how good they are in giving us an indication of how far the goal is, as opposed to how hard they are to compute. So we want to balance the computation cost and the informative value of a heuristic. So far, so good. Any questions about that? Hopefully you guys are familiar with at least the basic concepts. How does this translate into our world? So goal recognition design problem is defined as using an initial goal recognition model where we have an environment, which is defined as a planning environment in which agents act. But as opposed to planning, we have several goals. Remember that, right? The planning problem has a single goal condition. We have multiple goal conditions that we want to distinguish between. We have agents. In our case, they're going to be bounded suboptimal agents, which, of course, optimality is a special case of. And we have the recognition system with its sensor model, how we have a mapping from how agents behave to how their behavior is perceived by the recognition system. The second element is the design model. And it was very easy. I mean, design models can be defined in various ways. Coming from the planning world, it was very easy for us to define the design models as a set of modifications. As a set of modifications and a transition function that defines the effect of change on a model. Yeah?
So with the design model, do you need to know about the environment it works in?
Yes.
Or are those completely separate?
No, that's a good question. So the transition function is defined. Sorry. The transition function is defined by modification and the recognition system on which it is operated. So the environment is here in the recognition system. And it results in a different recognition system. Okay, so that's a transition between recognition systems. And basically what we're trying to do here is to find the best recognition system for our, that minimizes the worst case distinctiveness. Thank you for that question. We also have design constraints. Okay, so we have a mapping for a modification sequence. So sequence of modifications, a given initial environment on which we apply this sequence, and a validity score. Or here we just have a 0, 1, whether a modification is valid or not. Example for a constraint is a budget, right? Anything more than 4 is not valid, right? Or whatever the application. The idea here was to define a general model for design. So the observable projection, right? This induces a set of possible behaviors. We have a sensor model of the observer that defines how behavior is perceived. A non-distinctive path, this is just establishing a terminology. A non-distinctive path is a path that doesn't reveal the goal of the observer, and we are interested in finding the worst case distinctiveness. So let's see this in our example. The observable projection, let's take this, the observable projections of path, because I didn't state otherwise, is just the paths themselves, but we could see fragments of the paths as well. The non-distinctive path is basically, for example, this path here. Why is it non-distinctive? Because it's a prefix to a valid plan to both G1 and G2. And this defines it as a non-distinctive path. The maximal non-distinctive path is just the non-distinctive path with maximal length, right? So any behavior on this path is non-distinctive. The maximal one is the one that reaches the wall. Those are the terminologies. Hopefully, yeah.
So why do you want the worst case? That part isn't clear to me.
What we want is a measure of how good an environment is. So we're doing offline design. We are analyzing an environment. And you're right, why worst case? We could, and William is going to talk about different measures. But what we had in mind is a setting where, well, our motivating examples was basically a security setting where we said, well, if we minimize the worst case, then we're maximizing the distance between the goal and the furthest point the agent can reach without us knowing what the goal. So this worst case analysis gives us a buffer zone around the goals that help us react, right? If we want to understand who are the agents that are going to G1, if we measure the worst case setting and minimize that, then we're maximizing the ability of the system to react. Does that make it clear? Yeah, because remember, we're not talking about a specific agent. We're talking about an environment. There are no agents. When we're analyzing, we're just looking here and saying, what would be the worst case? And if we minimize the worst case, so it's a min-max situation. If we're minimizing the worst case, we're providing guarantees. This is Erez, who was my PhD advisor for this work. One of them.
I have 2 talks.
No, I know. I didn't expect you to be here. You know all about this. So how do we? So was that clear? Yeah, great. So how do we find the worst case distinctiveness? And now that you will see the techniques, you will maybe think that we first came up with the techniques and only then with the measure, but actually in this case, we actually did want to find the worst case distinctiveness, and we found compilations to planning to be an effective way. So how do we compute this worst case distinctiveness path? We have a planning model of the agent. We have the set of possible goals. How do we compute the worst case distinctiveness? So one way is, of course, to just exhaustively explore all the paths. Remember, planning gives us a planner. If we take this to a planner and give the goals, like just for example, let's just play around with this thought exercise. We have the planning model of the agent. We have a set of 2 possible goals. We could have just gave the planning model with one goal, the planning model with the other goal, and computed the WCD, right? We just check the prefix. What's wrong with that? problem is that a planner only gives me one plan. If there is multiple optimal plans or multiple valid plans, the planner doesn't give that to me off the shelf, right? The planner gives me one plan, doesn't give me all the plans. And we want to account for all possible behaviors because there are many ways to achieve goal one, right? There may be exponential number of paths that are possible. We want to account for them all, and we want the worst case. So how do we do that? If we do that exhaustively, exploring, just the BFS exploring all the possible paths, that doesn't scale, right? So what we did was we found a way to compile goal recognition design into planning. Now, usually when I give this presentation, I skip this, but since you are an ICAPS audience, I'm actually going to dive into the details because I think this is super exciting. I always am super excited when I can do something new with or the off-the-shelf planners that are available. So the idea here in this compilation is to take goal recognition design and compile it into planning. Now, goal recognition design has one agent, two goals. Planning has one agent and one goal. How do we bridge this gap? What we did was actually we created a compilation where we have two agents, each with its separate goal. So agent 1 is aiming at goal 1. Agent 2 is aiming at two goals. And my goal, my single goal, because for a planning problem I need a single goal, my single goal is for each agent to achieve their goal. How? Okay, so I have two agents in one planning problem, each trying to achieve their respective goals. How do I make sure that I find the worst case distinctiveness, right? If I have two agents in one planning problem, they can still each achieve their goal in an optimal way. What we did here is introduce an option for the agents to act together. Okay, so instead of walking separately, they can walk separately, but they can also walk together. And when they walk together, the compilation provides a very small discount, an epsilon discount, small enough to make sure that agents don't divert from optimal behaviors. And when they perform actions together, the actions together are epsilon lower than performing alone, and that's how we find the WCD with one call to a planner. Okay, so we take a goal recognition design problem, and we create a copy of the variables for each agent. Now remember, there is no real agents. It's just different agent models, right? I don't really have two agents. I have one agent. But the agent has two possible behaviors, and they both start at the initial state, right? They each aim at their goal, and they act separately or together by providing the discount. And this way, the single call to the planner reveals this path. Okay, so a little bit of strips, because just to kind of ground this into something that you guys may know, we take the grid navigation problem, which, that's just the typical, right? We have connected places between which agents can move, and we just have the move action, all of this. The difference in when we create a GRD problem is that the problem looks pretty much the same as a regular PDDL, but the goal here has a missing part, right? We have different possible goals, which are just defined in a separate file that defines the different goals, right? This is goal 1 and goal 2, right? We have different hypotheses that are possible. And then we compile this into a two-agent problem. So here we have two agents, right? Agent 0 and agent 1. We have predicates that are now have the agent component in them. And we have a predicate called split, which indicates whether the agents are allowed to act together or not. They are only allowed to act together because we want a prefix. They're only allowed to act together in the beginning, right? Once they split, they can't split anymore. And this is the interesting part. We define the move action now has 3 instantiations. One for moving together, right, when they are, before they split. Then, and here the cost you can see, yeah, this is, of course, we need, because planners only support integers, so we needed to factor the cost, right? And then we have moving separately, which is only for agent 0, with a cost that is epsilon higher. That's the basic idea. And sending this problem, the problem is, defines the goal for each agent. So agent 0 has to be in place 4, and agent 1 needs to be in place 0, 4. That's the idea. So sending this compilation to the fast downward solver gives us the worst case distinctiveness path. Yeah.
The WCD path or plan, that should also be one of the optimal plans for each of the goals?
Yes, this is because we are assuming here that we are, so here we were assuming that agents are optimal. So the solver will produce necessarily, given the epsilon, if the epsilon is small enough, not to so to make sure that agents are not encouraged to divert from optimal behavior, the behavior is optimal. Now, in fact, we have, I'm going to show this, but our compilation, I showed you the compilation for classical planning, but we have compilations that account for suboptimal agents, for agents with for observers with partial knowledge, and so I'm going to specify for agents that want to maximize their privacy. Actually, yesterday, our JER paper came out with all the details about kind of the different variations of the compilations. So before I show you the variations, how do we minimize the worst case distinctiveness? We want to guarantee optimality, right? We want to make sure that we are finding the optimal solution. So how do we guarantee that? We are, of course, again, assuming that our space of modification is exponential, and we cannot explore it exhaustively. If you can explore it exhaustively, then just do that. We don't need all these techniques, but we are looking at situations where this wouldn't scale. So how do we do this? An effective way for us to think about it was to think about this as a search in the space of modifications. So we are doing design, and we want to understand each node, which is the search space is what we have above the blue line. Each node in our search represents an environment, a change that we could introduce to the environment. And what we want to do is either heuristically search this space or prune any irrelevant modifications. So what we did in our first work was to show that basically worst case distinctiveness path, the actual path that maximizes the worst case distinctiveness is one where we could focus our search. So instead of looking for all modifications, we only looked at modifications that actually change this path. For example, block actions on the worst case distinctiveness path. Why is this working? This is, we presented the work in 2014, but it only took us until 2018 to actually understand why this working and why this is working in a more general sense. This is working because these type of modifications form a generalized strong stubborn set. So there are a lot of people around here that can tell you more about that, but the idea is that this guarantees that we are preserving optimality by focusing on the path that maximizes the worst case distinctiveness path. The reason why this is working is because our models are independent, persistic, and monotonic, which means that basically where we are applying change, the order doesn't matter. They are persistent in the fact that valid sequences can't have invalid prefixes, and they are monotonic, non-distinctive in the sense that if we block an action, we are necessarily not increasing worst case distinctiveness. I don't want to go into too much of the details, but what I kind of wanted to show here is that by generalizing, by understanding why this works, we were able to actually support not only all existing GRD models, but also new types of modifications. So this allowed us to support settings where the system has partial information. And a very intuitive understanding here is that more sensors are always better for the recognition system. But remember that I showed you that we blocked actions, right? We build walls. We can't always build walls. Sometimes we have to introduce more subtle forms of change. So let me dive into this example also because I've been talking a lot of theory and I want to kind of break it. So let's look at this example. This is a blocks world example where we have a robot that is moving blocks around, right? You know, and if anybody here is not familiar with the blocks world, let me know. But the idea is that there is a hand that's a robotic hand that is trying to build some sequence. And remember, this is not planning, it's a goal recognition, so we have two possible goals, right? So in this case, we have these blocks here, and we know that the agent is trying to achieve either A on C or C on D. So far, so good? Yeah. What is the worst case distinctiveness in this case? What makes recognition difficult in this case? If we are observing this setting, the problem is that block D needs to move anyway, right? In order to achieve A on C, I have to move D, I have to move B, and then I can put A on C. So D needs to move. In order to achieve C on D, I also need to move D. I have to take D, put it on the table, and then put C on D. Problem. That's WCD1, or however you count your actions. So D needs to move anyway, and that's a problem for us. We want to make sure that basically this is a problem for us because when we see D moving, there is nothing we can actually see. Now let's make this even harder. Let's put this in a box. So now the robot is in a box. We don't even see the actions. We just hear the actions. We just hear the movement. We know how long it took to perform the task, but we don't even see which blocks are moved. In this case, recognition is even more difficult, right? Because we are just basically, the agent can achieve its goal without revealing it to us. Now we could put sensors. What does it mean? We can just a motion sensor on one of the blocks. And let's say we have a budget for that, right? We only have one. Where would we put the sensor to minimize the worst case distinctiveness in this partially observable case? What would help us? So putting it on D is useless, right? Because we know that D has to move anyway. So if we put it on D, we know D has moved. That gives us no information. We would put it on B, right? Okay, so if we put it on B, maybe block D moved, but as soon as the second action occurs, we know what the goal is, because block B needs to be moved only for achieving goal number 1. So far, so good? Good. So what do? We are not happy with this situation because still block D can be moved first, delaying recognition, and we want as early as possible recognition. What do? We introduce constraint. Oh, one more point to make here is that if we block an action, right, we just disallow an action from the model. Is there an action that we can disallow, making sure that the goal is still achievable? The answer is no, right? We can't just remove actions, which is what we did with the fountain, right? With the fountain, we basically just made sure that the agent can go straight. So what we do here is we introduce constraints. We say, in this case, we exploit the fact that block B is smaller than block D. And what we introduce into the robots model is a constraint that disallows extending the hand. Contracting the hand. You can only, the robot starts by its hand contracted, but you can't, after you extend it, you can't contract. We just introduce an artificial constraint into the robots model, and now the robot is forced to first pick up block B, and only then, is forced to first, if it needs to move block B, it will do it. It will be the first action. So by putting a sensor on block B, we know that if it moved, then it was goal 1. If it didn't move, it's goal 2. Okay? So think of this in a more general scale where you have a intelligence problem where you have like multiple agents and you have specific sensors that you can place. GRD helps you understand what is the critical information that you need to get and where to place your sensors. That's the basic idea. So what I covered so far is our work from ICAPS 14 and Sonnet Al's work from AAAI 16, where they modeled goal recognition design as a answer set programming problem, and they managed to beat our techniques by far. So for fully observable settings, answer set programming proved to be more effective. But later on, we extended our models to support different kinds of agents. So for example, AAAI 15, we supported agents that are bounded suboptimal, and still we used classical planning techniques to, I showed you one compilation, but we extended the compilation to support bounded suboptimal agents. Then for AAAI, ICAPS, and as I said, as of yesterday, GER 19, we supported, oh, sorry, I didn't explain what this table was. Sorry for that. Let me explain to you why we have the table here. This is a table that William constructed for you guys to understand how goal recognition design literature evolved. So here we have the definition of the agents. Then we have the definition of the environment. So agents can be optimal, suboptimal, have partial observability. We're going to play around with that throughout the tutorial. We have an environment which can be either partially observable and also have stochastic actions, also partially observable from the point of view of the recognizer. We have different matrices, as you guys suggested, that can be effective. We have the worst case distinctiveness, and William is going to talk about the ECD. And then we have different ways of introduce design, right? We talked about action removal, where we remove actions from the model, but we also have sensors that we can place and action conditioning. So the following work that we did was to support agents with partially informed partially informed recognizers, where we have partial sensors, right? So the same technique, or we had to extend the techniques, but GRD applies to setting where we have partial information. We don't have perfect observability of the acting agents, and we can place sensors to make sure where would we put the camera in the airport to make sure that we recognize the goals of the agents as effectively as possible. We then had a model for improved privacy, so design for improved privacy. So far, we talked about goal recognition design from the point of view of the recognizer, right? We see the recognizer sees the agent is agnostic to the recognition process, but what if we want to, what about the agents? What GRD actually provides, and what we realized for our ICAPS 16 paper, is that we can use the same techniques when we compute the worst case distinctiveness, but instead of using them for the recognition system, we can provide that, we can give that to the agent. So it's a way to compute a plan that maximizes privacy, right? So maximizes privacy in the sense that the maximal number of steps, when we reveal the worst case distinctiveness path, we tell this agent, hey, if you walk all the way up to the wall, you will conceal your goal as much as possible. I finished earlier than we expected.
So what I just realized was that halfway while Sarah's going through is that when the tutorial chairs assigned us the slot, they told us that we'll have 3 hours. 1.5 hours before coffee break and 1.5 hours after coffee break. And then today when I saw the schedule, we actually have 2.5 hours before coffee break.
Perfect.
So we actually have an extra 1 hour. Otherwise, we were supposed to start at 9 instead of 8. So that's why I guess we ended up an hour early, because this is supposed to be 1.5 hour material.
Yeah.
So I guess the question now for you guys, since this is essentially for you guys, do you want us to continue and up to coffee break and then maybe leave for lunch earlier, or do you want to have a longer coffee break? So this is where we need to recognize your goals. And I need to ask, now this is an online design problem, right? What question should I ask so that I can effectively recognize your goals? So, right, so think about it, and I'm going to ask you to raise your hands. That's the easiest way. Right, so should we continue? Then we have an early lunch break. So lunch break then starts at whatever. We're supposed to have lunch at 12:30. We can then end early at 11:30, right? Or do you want to have a long coffee break starting now? All right, who wants longer coffee break? Who wants longer lunch break? Right, lunch break wins.
Yay.
All right, so I'll then continue with the second part. Do any of you guys need a bathroom break? I guess we need that if we have time for that. So let me see. All right. So I'm going to talk about now basically stochastic domains. And following up on this table that Sarah presented, this work was essentially what Christabel worked on. Was presented at ICAPS 2016 and 2017. And this is the same outline, I guess, as Sarah talked about in the deterministic environment. We'll talk about some backgrounds, defining what exactly the problem is, how we complete WCDs. And it's going to be slightly different up here. But how you minimize WCDs, the same ideas of pruning and so on, is going to be very, very similar. And I'll show you some sample results. And as usual, ask questions, right? Okay, so in Sarah's in the deterministic environment, the agent that was acting in the environment was essentially using some script formulation or PDDL that you saw, right? When the actions of the agents have stochastic outcomes, now that doesn't really work anymore. So what we did was we modeled it as an MDP. An MDP, hopefully most of you are already familiar with it. It has a bunch of states and actions. There's some transitions for, if you take a particular action from state S1, we will end in state S2 with some probability. So that's essentially what the transition function tells you. The cost function then tells you, all right, if you take this action from S0 and you end up in S1, what is the cost? You can also have a cost function where, so this is the most general cost function that depends both on the state that you are taking the action from and the resulting state that you end up, right? You can also have cost functions where I only look at, state action pairs over here. I don't care which state you end up. No matter what the successor states are, the cost is the same for everything. Or you can also have actions that, you can also have costs that maybe it doesn't depend on action, just depends on state, right? So if you're a particular state, you incur a cost. Whatever action you take, when you get to a different state, you incur a different cost, right? So this has a different forms over here. And then G basically then is a set of goal states. In a traditional MDP, you basically have G is a particular goal state, right? And S0 is the starting state of the agent. Mapping it to a more example that's more easily visualized, right? Imagine a grid world. So these are images that I stole from the Berkeley AI course. So I teach an AI course at WashU, and I use this figure, and I thought it was very intuitive, so I'm using it here again. So if you're familiar with MDPs and how they are, feel free to go have a bathroom break or take a nap for the next 5 minutes, right? I'm going to talk about stuff that you should be familiar with already. Right, so imagine that you have a grid world, you have a 4x3 grid, right? You're a robot, you want to basically start at this cell, bottom cell up here, and you want to get to the top right cell up here because you want to get this treasure that has a large reward. And these numbers over here, now this shows rewards instead of costs. You can think of rewards as negative costs. So a +1 reward corresponds to, let's say, a -1 cost, something like that, right? And you want to maximize your reward. And there's a wall here that you can't get into. And there's also a pit here that if you fall into, you incur a really negative reward or a really high cost, right? So this is bad, this is good, right? And mapping this to MDPs, then you can think of the cells of this grid as states. The actions of the robot could be in the 4 cardinal directions, north, south, east, and west. The transition, so let's say this robot has faulty wheels, it can potentially slip, right? So if it tries to move forward, it has an 80% chance of successfully moving forward. But sometimes left wheel slips, it goes to the left, and sometimes the right wheel slips, it goes to the right. And this also has probability with a small, let's say, probability of 0.1 to go to either left or right, right? But it never slips backwards, right? And here the rewards would be the simple version of the rewards, where if you are at a particular state, you would have a reward. So if you get to this goal state here, you get a reward of +1. If you get to this pit here, you get a reward of -1. And every other state that you're in, you have a reward of, let's say, -0.1. And this is what they call a living cost. So this is, this is there so that, this robot cannot walk around in the environment forever. You will want to eventually try to get to the goal as quickly as possible, right? And then goal states, initial states are pretty obvious. Right? Okay, so, and the key difference between what Sarah talked about in the deterministic environment and what I'll talk about in the stochastic environment is essentially the outcomes of the action. Right? In the deterministic environment, if you try to move forward, you are sure you will end up in the next cell in front of you, right? 100%. Stochastic environments, now if you try to move forward, 80% of the time you succeed, 10% of the time you move left, 10% you right. So now when you take a particular action, you might end up in multiple possible states, right? All with some non-zero probability. Right? And this would be the key difference between what Sarah has done and what we have done, right? Okay. So now that you know what an MDP is, a solution to an MDP is essentially a policy. What Sarah has in a deterministic environment, a solution to, say, a path planning problem is a path, right? Because you know that if I'm a starting state, if I take action A0, I know exactly what the next state is, and if I take the next action, so you just need to know what is the sequence of actions to take until you get to the goal. In a stochastic environment, you can't have a sequence anymore, because if you take the first action, you might end up in 3 possible states, right? And maybe if I end up in this state over here, I want to go left. If I end up in this state here, I want to go up. If I end up in this state here, I want to go right. So now the second action that you take depends on where you end up, right? So you cannot have a path anymore in the traditional sense. So therefore, we have this thing called a policy that basically is a mapping from states to actions. It just tells you that, all right, I don't care how you got to the state. If you are at this state, take this action. Right? And that's what a policy is. We'll look into how we can compute that later, but the intuition of what a policy is for this, like this, right? So imagine if, let's say, the living reward is -0.01, right? So this is a small living reward. This green arrows then shows what is the optimal policy for this problem. So you can imagine that, so this kind of makes sense, right? So if I'm in a starting state, I will try to basically take this route to get to the goal. And most of the time I probably successfully get there because there's a 80% chance that each of my actions gets me to where I want to get to. But let's say if 10% of the time I ended up here, now I want to get back here so I can get to this route. Okay? You have a question? Or? Okay, right. And then you can see this actions over here, then this one would be interesting because you would think that if I'm here, my optimal action should actually be to go up and get to the goal as quickly as possible, right? But here the optimal action actually is to go left. And the reason is if you go left, let's say if you go left 80% you move forward, and in this scenario if you hit the wall, you end up in the same cell that you're at, right? And this is a good action because this means that there's 10% chance you go up, you could go this way, right? And 0% chance you actually end up in a pit, right? So this is a very safe action to take. And because this value here, this is a -1 reward, is quite much worse than the living reward. So therefore, this robot is willing to, try and basically be very risk averse to try to get to the goal, because taking actions that doesn't work, it incurs only a very, very small cost. Right? And if we increase the cost slightly, basically the living reward now is a little 3 times bigger. Then this is the optimal policy now. You can see essentially it's very, very similar to this one here, right? Except that, here instead of going left, now you want to try to go up. Because now it essentially says, if the cost of living is a little bit higher now, maybe I'll be a little bit more risk-seeking because I want to get to the goal faster. If I do it this way, I will get to this eventually, but it's going to take me forever, right? And that difference is larger than basically the difference in the living and the cost, the living cost. So now I want to get this way to get here, and this policy is also changed, so you want to get this way faster, right? Yes?
What's the policy if you accidentally get into the pit?
Oh, game over.
Just stop.
Yeah, so let's say there's a terminal state and there's no action to get out of it, right? Good question. Okay, so you can imagine now, let's say if I make the living reward even worse, so it's even more higher now. Now you can see this policy on this side stays the same, but the policies down here changes. So over here you can imagine that the agent is still trying to basically get over here and take the long path here. Now if the cost is higher, now if the agent basically ends up here for some reason, is willing to take this shortcut that is a little bit more dangerous, right? And this is the worst case, where now the living reward is even worse than this. And here's important to see, because this living reward is worse than the pit, right? This is like, there is no point living anymore. Every day really, really sucks. Dying is better, right? This is this scenario here, okay? And then, so you can see what optimal policy here is that, all right, if I'm here, going up here and up here, man, it's like cost of 2, plus 1, cost of 3, that's pretty bad. Coming down, jumping in here, cost of 3, also pretty bad. You know, let's just jump, right? And just commit suicide. So now you can see that the optimal policy of the problem can change quite dramatically depending on how you essentially define the costs, define transitions, and so on and so forth. And that's and this is an example of what a policy is, right? Questions up to here? Right. Okay, so now that you know what the policies are, how you compute them, and here's where there's some technical equations. Let me see this one here, right? So to get the optimal policy, the first thing we need to do is to find a way to evaluate how good a policy is, right? To put a value to that policy. So you want to compare policy A and policy B. You want to say policy A is better because it has a higher value, right? So you need to define what the value of a policy is. And a value of the policy is basically defined using this equation over here, right? It is a recursive definition. So you can imagine that if you are at a particular state S, the value of this policy at this state would be the expected the expected cost. So this is the expectation of, if I execute this policy, if I execute the action prescribed by this policy at this state, I will end up in state S prime with some probability. So this is, let's say, some probability over here. If this is deterministic, then this is the successor state, right? This is 1. And then this would be the cost of taking this action from this state and getting to the successor state, right? So this is the cost of the action, and this is whatever the optimal value is following that same policy from the successor state. Right? So if this is a deterministic action, then this would be 1. You don't have to sum, actually it should be S prime here. S prime here, so that's a typo. Then S prime would, you only have one successor state. The optimal value of the state would just be the cost of that action plus whatever cost from your successor state onwards to the goal, right? So if it's the deterministic action, then this value becomes, this policy is then the path length. Right? But in a stochastic setting, now you need to take the expectation over all possible successor states and all possible and the associative cost. So so this is the definition for the value and of a particular policy. And then for the optimal policy, then you basically just look at between all possible actions that you can take from this state, pick the one that has the smallest cost. Right? So then this is Angmin here, because then A is basically over here, and then this will tell you, all right, this is the best action to take from this state S. Questions up to here? So this is traditional definitions of MDPs and value functions. And to calculate, so this is the definition, and to calculate this, there's this algorithm called value iteration that you can calculate recursively until it converges. This is something pretty standard, and there exists lots of Python packages and things that you can download to do this very effectively. I'll not get into this, right? Right. Just know that there exists an algorithm there exist multiple algorithms that can compute these things. Okay. All right. So now that you guys are all MDP experts, that's the background. Yes.
So just to clarify, if the action or the policy that's provided is one that is,
loopy.
Little bit smaller than like a more optimal, one that is just more optimal in the sense like it's quicker, faster. The output when it's minimized, it's still the one that takes up more time. Is there a way to kind of
So okay, so let me see. So I guess the first question is, let's say if there's a policy that loops around, right? Kind of maybe there's an example over here, maybe. No, there isn't. But imagine, let's say, if this was pointing downwards and this was pointing downwards. Let's say, right? Then this policy, you basically say, all right, try to run in circles, right? And yeah, right. So if you go that route, then evaluating this policy, you can imagine that the cost will be higher than this one that ends up here faster, right? Because of that living cost. And because this thing is calculated recursively, essentially, it will keep on running this until the base case would be when you get to a goal state, or you get to a state where there are no more actions. And that policy where you run around is now going to have a higher cost than these policies here.
So it never would pick a policy that is.
Well, if you're looking for an optimal policy, then you'll never pick that policy. Depends on, again, so this is just defining the value of the policy, right? And usually in MDPs and so on, you want to find the best policy or one optimal policy, and this is one way to do it. And similar to how the deterministic environment where there might be multiple optimal solutions, right? Similar here, there might be multiple optimal policies, all equally good. And this will just return one of them. So this is like the A star variant for stochastic environments. Any other questions? All right. So now that we know what MDPs are, let's look at something to motivate why GRD is really, really cool in the stochastic environment. And how many of you guys are familiar with Harry Potter? Right, presumably almost everyone. And so this is going to look very familiar to you. And when I was watching this video last night, I just saw, oh, this videos were made, I mean, the movies have been out for so long, they can see how old the actors are. So let's say Harry Potter, there are two key things in Harry Potter that could be combined for GRD. So this is one of it. So hopefully. So this is, I think, the first movie.
It's spooky. She knows more about you than you do. Who doesn't? Look! What's happening? The staircase has changed, remember? Let's go this way before the staircase moves again.
All right, so this is ingredient one, moving staircases. And then the second one where Harry is now a lot older.
Greater than ours. George, if you will. I solemnly swear that I am up to no good.
Messrs. Mooney, Wormtail, Padfoot and Prongs are proud to present the Marauder's map.
We owe them so much.
Hang on. This is Hogwarts. And that... no. Is that really...
Dumbledore. In his stunning pacing, does that a lot.
So you mean this map shows...
Everyone.
everyone?
Everyone. Where they are, what they're doing every minute of every day.
Brilliant. Where'd you get it?
Nicked it from Filch's office, of course. First year. Now listen,
All right.
there are 7 secret passages.
So that part is not important, right? How they got it. But essentially, with those two things combined, now, there you go, full screen mode. Right, with those two things combined, imagine now that you are Severus Snape or Dumbledore, right? You have access to now this Marauder's map, and you can see where all the students and all are moving around. And you could say, all right, you see Harry Potter wandering around in the alley. You're trying to figure out where is Harry Potter trying to go. Right? Where is Harry Potter's goal, right? Is he trying to head to Albus Dumbledore's office? Is he trying to head to the Gryffindor dorm? Is he trying to head to the Hall of Requirements? And you can see him move. And unfortunately, in Hogwarts, the staircases move. So just because Harry took this staircase, which at that time might be heading there, the staircase could move. Now Harry has to basically end up there. So the moving staircase then kind of models stochastic action outcomes, right? And you can combine them basically, then you can see how it becomes a goal recognition problem of trying to recognize where Harry Potter is trying to go in an environment where the outcomes are stochastic, right? And I think one of our later papers used this Marauder's map scenario as our motivating application. Right? It was a workshop paper, so it was kind of fun. Right. So imagine now, instead of just recognizing where Harry Potter is trying to go, now if you are, maybe the Ministry of Magic, you could slightly design Hogwarts, place walls or do certain things. How we want to do it so they can recognize the goals of students moving around better. That's essentially the goal recognition design variant of this problem, and the outcomes, and then the environment is obviously stochastic. So the model that we are talking about is called Stochastic GRD, or SGRD, and this is going to look very similar to what Sarah has talked about. The key differences are that over here, instead of strips or deterministic models, now you have MDPs. We also assume that the agents are optimal agents, so they will try to find an optimal policy and execute according to that optimal policy. Recognition system is exactly the same as what Sarah has talked about. You can observe what the agent is trying to do, or what the agent is doing, right? And the modifications are also very similar. You have a set of possible modifications. You can do certain things that changes the recognition system to a different one. And you might have a budget or a set of possible modifications and so on and so forth, right? Right. So, and then I'm going to use this state action graph essentially to illustrate what SGRDs do. So where the circle, so these circles, these nodes are states, which could be goals. So goals are G0, G1, and G2. The starting state of the agent is at S0. And these arrows are essentially actions that they can take. And these actions, some of them have two outcomes. So for example, A0, if you take A0, you have a 50% chance of ending up here, or 50% chance of ending up here, right? And this is, for simplicity, this is the only stochastic action in this example. Everything else is deterministic. So for example, over here, if you took action A4 from S1, you're guaranteed to get to at G0, right? And you'll see also that some nodes and edges or arrows are bolded and some are not. Essentially, the ones that are bolded are the ones that we need to care about. The ones that are not, we can ignore them for now. So if, let's say, the starting agent, if the starting state is over here, and if the goal of this agent is to get to G0, then you would see that the optimal policy, and these are the actions that the agent will have to take to get to G0, right? These other nodes that are not bolded, essentially these are states that the agent will never reach. They're not reachable states, and these actions are, actions for that the agent will never take, right? And what we call here this set of legal policies, if the agent is optimal, then this is the set of optimal policies for a particular goal. And it could also be a partial policy. So in this case, it is a partial policy. A complete policy is a policy for every state. A partial policy is just a policy for some subset of states, right? So if the goal is G0, then these are the rate actions that they want to take. If the goal is G1, now you can think that the actions that they want to take is slightly different, right? If the goal is G2, the actions that they want to take is slightly different again, right? So then if you want to recognize the goals of the agents, right, we want to see what actions they can take and so on, and we want to define WCD using that information. It would be ideal if we could observe the policy of the agent, right? If we could see somehow magically, if I could know, if the recognizer could know what is the action that the agent will take for all possible states. If they can observe the policy, that will make things really, really easy, right? But we obviously can't, because what we can observe is where the agent is, what state it is, maybe what action it took, and what is the resulting state, right? And I only know the actions of the states that the agent actually end up in. So I can only observe essentially the agent's trajectory of what the agent has done so far, and we have to use only this information. And later on, you will see that in some cases, you might not even be able to observe the action of the agent. You can only observe where the agent is. And this could be, say, in a robotics application, right? You see where the robot is right now, and then one time step later, you see the robot is here. You have no idea the robot was trying to move forward or was trying to move left and accidentally slipped to forward, right? You can't tell, right? So you can't observe actions. So if you can't observe actions, then it becomes even harder, and we'll see the impact of that later. And so now if you can observe trajectories, we using Sarah's definitions of non-distinctiveness, we say that a trajectory is non-distinctive if this is part of an optimal trajectory for multiple goals, because then I can't tell which goal you're trying to get to, right? So for example, if you're at S0, A0 is the only action from this state. Therefore, it is the optimal action for all goals. Right? So if I see you're at S0, I see you execute A0, I see that you end up in S1, your set of possible goals are essentially all the 3 goals, right? G0, G1, G2. But if you are here, if your goal, and I see you execute this action and you're here, I know now your goal is definitely G1 or G2. It is not G0, because if it was G0, you would have executed action A4. Right? So here's how we can start off with the set of all possible goals of the agent and somehow reduce that based on observations of what we could see the agent is doing. Right? And then from here, essentially, the next action the agent takes will reveal its goal completely. Right? If that goal is G1, it would take A2. If the goal is G2, it would have taken A3. So this is the furthest the agent can get this way without revealing its goal. Right? Now, let's say slightly different. So let's say it's a different scenario where, again, let's say the agent took A0, but instead of ending up here, the agent ended up down here. Right? Now, the set of possible goals are now, again, all 3 goals, right? Because this was the optimal action for all 3 goals. And from here, if the goal was G1, you would have done this. But if the goal is G0, G2, you would have taken this. So you would basically end up here. So in this trajectory, this would be the longest sequence of actions the agent can take without revealing its goal. Right? So now you can see that the sequence and so on depends on the whole history of the agent, on what exactly, which path it took and so on. And a key observation here is that if you see that the agent is in S2, right, and if you didn't know how it got to S2, whether it went this way or went downwards, right, you can't tell whether the goal is this one or this one. It could be both of them. Right? So essentially, after looking at this scenario, what we found out was that the set of possible goals now is no longer Markovian on the state space. Right? Just by observing the state, you do not know what is the set of possible goals. You need to observe essentially the whole history. Right? Okay. And then, so now that you know what trajectories are, we want to have a way to measure, all right, how bad is a trajectory. So we have this notion of cost of trajectories, similar to in a deterministic setting. A cost of, let's say, a partial path is let's say, the number of actions along that path, or the cost of the action along that path summed up over the sequence. So partial policy here, the cost of trajectory here, you could have 2 different kinds of trajectories. You could have a trajectory where you have state action, state action, state action, and so on. If this kind of trajectories, the cost is very easy to compute. It's just the cost of these actions, right? You just sum them up over the trajectory, that's the cost of trajectory. If the trajectory is something like this, where you just see the states, S0, S1, S2, S3, S4, now this is a little bit more ambiguous because essentially there might be multiple state action trajectories that could result in this trajectory. So then you want to take the maximum over all possible such trajectories. It's the worst case. Right. Yes? Right, so then that's the cost of trajectories. And then, so in this example, this top one here, the cost of this trajectory is 2, because if you assume that actions cost 1 for all actions, for simplicity, then this would be cost of 1, so you get a cost of 2. This one just cost of 1, because it's only 1 action taken, right? And then policies. Now that you have trajectory costs, you also want to have how do you combine this cost of different trajectories into a policy, and it's essentially just an expectation over all the different trajectories if you were to take that policy. So if you look at this simple partial policy here, where you say if you're at S0, take A0. If I'm at S1, take A1. It doesn't define what the other policies are, what the other actions are, so this is a partial policy. Then there are only 2 possible trajectories. If you execute this policy, one is up here, one is down there, and the one up here has a 50% chance of happening because the outcome of this thing is 50%, and this is 100%, so it's half times 2 plus half times 1. right? So of course, if you look at a more complex policy and so on, where there are multiple possible trajectories, then you want to take the weight of, you want to take the cost of the trajectory multiplied by the probability of the agent actually taking that trajectory if it executes that policy, right? Okay, so now that you also have cost of partial policies, now you can compare policies essentially. So now you look at the set of all possible legal policies or optimal policies that are not distinctive, right, that are ambiguous. And the WCD then is the maximum over the cost of all these policies. Right, so if you have two policies, one is cost 5, one is cost 2, both of them are non-distinctive, maybe for different reasons, right, then the WCD is 5. So I'm seeing some potentially confused faces here or really bored faces. I'm not sure which one. Yeah.
In the previous case, the WCD was how the longest prefix before which it divided. Cost doesn't necessarily map to the longest prefix, does it? It could.
Right. So cost maps to the longest prefix if the actions are all uniform.
Yes.
But if they're not, then this could be not the longest, but the costliest prefix.
So the objective here would be to try and detect the goal to give you, the observer, as much time as possible to respond, right?
Right. So you can think of this as, instead of maybe the cost as in a number of actions, it could be, let's say, the time, the duration the agent will take to execute this action, right? In which case you want to, what's the longest time, right, the agent can hide their goal. So here, I guess we're using cost. You could define cost differently for different domains, depending on what exactly are important to you. If you want to, let's say, minimize, I don't know, so I guess, yeah, time and number of actions is probably the most common ones. But you can imagine, let's say, in a human-robot collaboration setting, you want to, cost could be defined in, the ease of executing the action, right? Like how much, I don't know, electricity the robot might have to use, or battery power, and so on. This could also be an objective. Right. Any other questions? All right. So the WCD here, the key note that I guess you guys have already talked about, and Sarah has mentioned it as well, is that this is measuring the worst case. It doesn't differentiate, what are the different goals of the problem, right? They treat all goals as equally important, equally likely, right? And we'll talk about a different metric later on that generalizes this. So in this scenario, so now we talk about how do you actually compute WCD. So this defines WCD. How do you actually compute it? And like I talked about earlier, the set of goals over here is not Markovian on the original state space. So and WCD depends on this set of goals, because if this set suddenly becomes 1, then that's an action that resulted in the goal being clear, right? So if the set of goals is greater than 1, it needs to be, the cost of this path needs to be included in the WCD computation. So what we then did is that, all right, the computation WCD is not Markovian in the original state space, but it is Markovian in what we call an augmented state space, where now we create this augmented MDP, where states are now not just the traditional states, but they are augmented with the set of possible goals for that state. So this augmented MDP would be corresponds to this problem over here. So when you start at S0, your set of possible goals are G0, G1, G2, all goals, right? So in the augmented MDP, your augmented state here, this is the starting state S0, and it has all 3 possible goals, right? And then you have an augmented action, and this augmented action basically says this is the legal or optimal action for these sets of goals. So since this is the only action, it is the optimal action for all 3 goals, right? And after taking this action, you could end up in 2 states, S1 or S2. So that corresponds to S1 or S2 over here, right? And S1, if you end up here, this is still 3 possible goals because this was the optimal action. And if you execute action A1, which is optimal for these 2, you get 2 over here. And at this point, the augmented MDP, I mean, you don't continue stuff down there because everything down here are actions that will reveal what the goal is, right? So the augmented MDP is only defined up to the point where the goals are ambiguous. If you came down this route, then this is the augmented state. And again, this basically corresponds to this part of the trajectory. Right. So part of the difficulty, I guess, that we came up with was that how do you actually compute, defining it is pretty straightforward, but you need to construct this augmented MDP, right, from this original MDP. And after you construct the augmented MDP, you can then use that to calculate the WCD. Right. So if you have this augmented MDP, then the WCD now is Markovian in the augmented state space. So the WCD over here is 0. If you came up here, then it's an action of 1, and a cost of 1, and a cost of 2 up here, right? So then, and this one would be cost of 1 and cost of 2 to come here. And then the WCD now is just the probability of the cost of the trajectories, right? So it's half times 2 plus half times 2. And you can compute this WCD using standard value iteration algorithms with a slight twist. In the value iteration algorithms, you would minimize the actions because recall that in value iteration, you want to find the optimal policy of an MDP in an MDP. And an optimal policy minimizes the cost, right? So therefore, you did this minimization. Over here, we don't want to minimize the WCD. We don't want to find the minimal distinctiveness. We want to find the maximal distinctiveness. Right? What is the longest sequence of actions the agent can take without revealing its goal? So therefore, we need to maximize instead of minimize. So therefore, we change this from min to max. And if you did this in a regular MDP, this would raise a huge red flag. And the reason is because if you did this in a regular MDP, where there might be loops in the graph, what you would get would be the value of every state, assuming every state is reachable from every other state, the value of all states to be infinity, right? Because this means that you could go to anywhere, you could go forever, you could have loops and so on, right? So you just accumulate costs infinitely, so then the value becomes infinite. So then you can't differentiate policies and so on. So this is really, really bad for traditional MDPs. But in our MDPs, we don't have loops. Right? Because we have this, each of these corresponds to a trajectory, right? And so we will essentially have a tree. So if you ran this modified version of value iteration on this augmented MDP, all is well and good, and you would actually get the optimal value, the maximal value at the starting state, and that would be the WCD. Right? Yes.
Two questions. So the augmented MDP would depend on your policy.
Yes.
Will S2 and S3 here be the absorbing state while you're doing value iteration?
Yes, right. Right. So to compute this, first I need to compute the optimal policy for every goal, right? Optimal policy for G. So like what I did over here, right? Like I need to find this policy, need to find this policy, need to find this policy, right? And then after that, I know that this action here is the optimal policy on all 3 goals, right? And that's how I can compute augmented MDP. So in terms of efficiency, this computation of optimal policy is pretty quick, right? And construction of this augmented MDP is also pretty quick. And WCD computation is also pretty quick. The part where it's hardest for us to scale is actually the design part, because this is just computing the WCD for a particular environment. Now I need to iterate through over all possible environments that I could get to from different designs, and for every possible scenario or every possible environment, I need to do all of this again, right? So that's this thing I need to do. Like if there are 100 possible scenarios, I need to do this 100 times, right? To find the scenario that has the smallest WCD. Questions? Yes?
The WCD here is really the expected worst case from a particular. So if there were 2 paths, not just one, as in this case, and one of the paths had probability 0.9, and there was another probability 0.1. If the 0.1 probability path was truly a lot worse, it may still not get the highest WCD.
Right. So you can imagine over here right now, right? This is with this augmented MDP, this maximization is not needed, because for every state, there's only one action that you could take. Right? So now in a scenario, you can imagine that let's say here A0, you could go to 0, 1, is optimal action for 0, 1. A1 is optimal action for 1 and 2, because you could have multiple optimal actions for the same goal. Right? Then you would have, maybe up here this is 2, down here it is 5, right? Then between these two of them, I want to take the maximum, then I'll get 5. Right? Mm-hmm. So the maximization again is on the actions that the agent could take at a particular augmented state. Another observation you could see is that you'll see that the set of goals over here will basically reduce as the trajectory goes further and further, because that kind of makes sense. The more an agent reveals its actions or its states, the set of possible goals becomes smaller and smaller, right? So you can't have, let's say, 0, 1, 2 over here, and then here becomes 0, 1, and then suddenly it becomes 0, 1, 2 again, right? So that's not possible. Right? Okay. So now that was WCD. This was something else that we thought about when goals are not equally important, right? In a scenario, I think someone had a question that, you want to detect if someone's going to the Mona Lisa or not, because that's really, really important, right? I don't really care if this person's going to this other painting that was done by a 5th grader, right? So you could have, different goals or priorities on different goals. Like, let's say in a security setting, you want to say, all right, if someone is trying to head towards this restricted area, that's really, really important to detect. If this person's trying to get to the restroom, I don't really care, right? So now different goals could have different importance or priorities and so on, and we want to take that into account. So we want to minimize the WCD for the part where the goals are important, and the WCD for the goals that are not important is not that I don't really care as much, right? So then you would have essentially a probability for each goal or a prior on the importance of the goal, and now you weigh the paths or the trajectories by these priors, right? And now you want to minimize what we call the expected case distinctiveness. Questions? Right? So this kind of makes intuitive sense, I think. Right? And then now, I guess I slightly talked about it earlier already, right? Now that we know how to calculate and the WCD and ECD and so on, how do you minimize it? Essentially, you have, the worst case, you have to enumerate through the space of all possible designs, which is really, really bad if the design space is very, very large, right? You could have, similar to what Sarah talked about earlier, on pruning techniques or heuristics and so on, right? You could also have that applied over here as well. So for example, like pruning techniques, if let's say I can block actions, yes?
Does the design space where you have to change your everything, does that also affect the probabilities of the actions?
No, so you can think that the design space would result in different environments, right? So you have a default environment, and you can calculate what's the optimal policy for this environment. If you did something, if you block an action, now you get a new environment, right? The optimal policy for this new environment is going to be different from this other one. It could be different from this other one, right? And in this new environment, because the optimal policies change, the WCD could also change. Right, so now the WCD now could be reduced if you block this action. The priors on the ECD and so on, this we assume do not change if you modify an environment, right? Mona Lisas are still important than 5th grade drawings, right? No matter how you design your museum, right? So you need to now, so some of these example of pruning heuristics could be, now if I want to consider blocking, I don't know, 2 actions, and I block this action, and it did a really bad thing by lengthening an optimal plan, and maybe that's a big no-no, then I do not need to consider blocking this action and some other action. Right? Does that kind of make sense? So I guess we missed this earlier. So when we started working on this problem, and we were thinking, all right, we need to minimize WCD. You could think that there's actually a trivial way to minimize WCD. For any problem, you can minimize the WCD to 0 immediately. How do you do that? You block the actions, all actions, from the starting state, right? If you had an initial state, if I block all the actions, right, WCD is 0 because the agent can't get anywhere. Right? So that's a trivial example, but that's a really bad example, because if we did that, then the agent can't get to its goal. So an implicit assumption in this GRD work that Sarah introduced is that we can modify the environment, but only if we do not block the ability of the agent to get to its goal, any of its goals, right? But not only do we not want to block the ability to get to its goal, we cannot make it worse than it was before the environment was modified. So if the optimal path length in the deterministic setting to get to a goal, or the optimal cost of the policy to get to a particular goal for the stochastic setting is 10, after the design, it cannot be larger than 10, right? And ideally, you don't want it to be lower than 10 as well, right? And that was how it started. And then as the literature progressed, we generalized the definitions to the set of possible modifications. So that the set of possible modifications essentially included only modifications that didn't have these restrictions, right? All right, so that's so pruning stuff and ordering heuristics, again, stuff that Sarah talked about with the strong stubborn stats and so on, right? You want to consider actions that cause the WCD in the first place, so we could also do something like that, right? You want to maybe consider blocking actions that are closer to the agent first, and if you can make the WCD smaller, you can use that for pruning and so on as well for later on if you use branch and bound techniques and so on, right? So this is something that will take the most time, and I suspect if any of you have awesome ideas, this is where contributions can be made, because this is where run times could be significantly reduced if you have really, really good ideas, right? And because this is the thing that contributes the longest to the run times. The WCD computations and augmented MDP constructions, those are pretty quick. All right, so some sample results. So unfortunately, I guess these graphs are kind of small. What you see are 4 graphs here. The 2 graphs on the left-hand side are for WCD. The 2 graphs on the right-hand side is for ECD. Don't worry if you're at the back and you can't read these numbers. They're not important, right? But the x-axis for these graphs are essentially the percentage of reduction. So 0 is on this side, 50% is on this side, then 0, 50%, and so on and so forth. And then the y-axis, this is the different rows of the lines here corresponds to different instance types, right? So you can see that, and then this is for 1 action being removed, 2 actions being removed, 1 action being removed, and 2 actions being removed. So you can see the observation is that, all right, there are some instances where WC and ECD can be reduced. That's great, but not all of them, right? Many of them, in fact, with only 1 or 2 actions, the WCD, for example, cannot be reduced, right? This might be situations where there's only 1 optimal policy to get to a goal, right? So if you did any changes to change that policy, then the cost could increase, or so on and so forth, right? So you don't really have a choice. You can only reduce WCD or ECD when there are multiple ways to get to a goal, all they are equally good, right? And the other observation, of course, is the expected one, where if you can remove more actions, then you can reduce more of the WCD, right? So here, only a few instances could have reduction. Here, more instances could have reduction. And where reductions are maybe 25% here, you go all the way up to 50% over here, right? And then the third observation you could see is that, all right, in some settings where WCD cannot be reduced, ECD could be reduced, right? Which kind of makes sense because, all right, maybe the worst case scenario, there's only 1 policy to this goal over here. But I can't reduce this. But I could reduce the policies for these other goals over here that are shorter, right? That are closer to me. So if I can't reduce the WCD, I should still try to reduce ECD. Right? Even if the probabilities of all goals are equally likely. So those are essentially some takeaway messages from this sample results. Questions up to here?
Yeah, we are.
Close to coffee time, I think, right? Is it close to coffee time?
No, it's still half an hour.
Okay, all right, good. So I can continue. Any questions? All right, so that was stochastic GRD. And next I'm going to talk about something that in collaboration with Sarah, we did last year called partially observable stochastic GRD. And this is the setting where outcomes of actions are not only stochastic, but the observer observing the environment has partial observability. So now as an observer, I might not know where you are exactly. I kind of know you're in this vicinity. So you can imagine that, let's say if I have a GPS satellite, right? I don't know your precise location, but I know, up to a certain margin of error, right? That's something that can be handled with partial observability. So how does that change? So again, this is a simple state action graph. So these are the states, and these are the two goals, G0 and G1. Again, the actions that are stochastic outcomes are only the initial two over here, that if you take A0, you have a 90% chance of ending up here, 10% chance of ending up here, right? And this thing is just a mirror image of the top one, right? So 90% going down here, 10% going down here. So in this problem, in the case where the environment is completely observable, so you can see exactly what actions they take, you know exactly where they are, the WCD is, what do you think? All right, if you're not sure, let's see if we can continue. This would be the optimal actions for this goal, right? If my goal is over there, this would be the optimal actions to get here, and this would be the optimal actions for G1, right? So which means that from the first initial state, the first action that you take, I will know exactly which is your goal already. Okay? And so in this setting, WCD is 0, because you can't hide anything, right? Clear? Right? Hopefully? All right. And then now let's say we make it a little bit harder. Now I can see where you are exactly, but I have no idea what you're trying to do. I can't observe your actions. So then your initial state, your goal is, either both of them. And if for some reason the next state I see is this, right? I have no idea how you got here. You could have taken the top path and ended up here, or the bottom one and ended up here, right? So I know the top one is for G0, bottom one is for G1, but because I cannot see what you did, I still do not know what your goal is. Right, so therefore goal is G0 and G1. And if you went down this way, this is the optimal action for both of the goals, so it's still 0, G1. And only after this, if you go up, I know it's G0, but by now it might be too late because you're already there. So if this is a security application, you already bombed your target. Yeah, I knew that you were trying to attack the airport, but the airport is already destroyed, right? So that kind of sucks. If you did down here, then I know what's your goal, but it might be too late. But if for some reason you ended up here, then I know that you got up here because this was the action that you took, right? So I know your goal, and similarly down here. So with unobservable actions, you will see that for every state, there's a set of possible goals. The WCD now is no longer 0, because you could have this sequence of state trajectories that I have no idea what your goal is. And the probability of this, the probability of this happening, it depends on which policy you took. If you took this policy where you tried to go up, right, then the cost of this trajectory, the expected cost is 0.1, because there's two actions over here, and there's a 10% chance. Right? Yeah, sorry, 0.2. Two actions and 10% chance, right? 0.1 times 2. And then here is also 0.1 times 2. So between these two policies, both of them is 0.2. The maximum is 0.2. So the WCD is 0.2. Right? And if, for example, let's say if this was changed to 0.5, then the WCD would be 0.5 times 2. Okay? So WCD went up when the actions are not observable. And now let's say we make it even harder, right? So states are also now partially observable. Previously, if you were here, I knew that you are here. But now let's say if you are in any of these three states, I can't tell the difference. Right? My GPS satellite tells me you are in one of these three states. What happens now? So you could be here, moving here, I can't tell. Or you're here, you're just taking a long time to take actions, I also can't tell. Right? So therefore, I will now need to combine for each possible observation the set of goals that are the worst set of goals that are possible, right? Or the union of all the goals. So this becomes G0, G1. This becomes G0, G1. Right? Now, if you did it this way, what's the WCD? the WCD now actually increases to 2, because you could have this policy here. If you took this action, is 0, right? If you ended up here, you could take another action, 1, right? So now the cost is 2. If you ended up here, you could take another action, right? Cost also 2. So now is 2 times 0.9 plus 2 times 0.1. So this policy's cost is 2. This policy's cost is just 0.2 from before. So the maximum of the 2 is 2, right? So now WCD increased from 0 to 0.2 when actions were unobservable, to 2 when the states are partially observable, right? So the key takeaway, I guess, in using this very, very simplified example is, the more uncertainty there is in the problem, as expected, the WCD becomes worse. Yes?
Question for you, backs up a little bit. Sarah mentioned something about sensor noise earlier, but didn't elaborate on it. Is that same partially observable?
You could think of it that way, right? It could be, so if the GPS setting that I was talking about, that's essentially just sensor resolution. Right, it might not be noisy. Oh, well, I guess you could treat it like it's noisy. I can't really tell the difference between which states and so on. So that could cause partial observability in the states from the observer's perspective. Mm-hmm. Yeah.
So, in like some of these really minor probability cases, it's like really bad because it's like you're at the goal because you're there versus you're still in the starting space. Is there any distinction between like those weird outlier cases where like most of it's kind of okay, except for this one thing, versus the like everything's kind of okay?
Right. So if you wanted to, so short answer I think would be you would need to look into what are the things that needs to be maximized for the WCD. Right. Each of these things that is maximized over, that's essentially one policy. So it could be that for one policy is really, really bad, for the other policy is really, really good. So if you look at all these breakdowns of expected costs, then that will give you a sense of how extreme is this scenario, right? If you just compute WCD. If you did ECD, then maybe if you knew in advance, like some goals are really important, some are not, then you could see how big or how small the ECD value is, right? But let's say to identify that, okay, maybe this right now, getting to, I won't be able to figure out the agent's goal is here until they get there. You would have to look into the WCD computations to see which policies it is that contributes to the WCD. It could be this goal, it could be some other goal, right? Yeah, but so far, to the best of my knowledge, like no one has looked into trying to have a description of, for all the different goals, what is the CD or the distinctiveness cost and so on, and maybe looked at that as a precursor to design. Questions? Any other questions? All right. Right. So this was essentially the key takeaway is the more uncertainty, the worse it is for the observer, right? And the design part is essentially could be to not mitigate the uncertainty, but to change, force the agent to reveal its actions earlier, but also in potentially sensor placements to reduce that uncertainty. So in this setting, right? So if I could only place one sensor that could tell me exactly whether an agent is at that state or not, I want to place a sensor right here, right? Because then if the agent is not here, I know that it's either in this blob or this blob or this blob. But if it's in this top blob, I don't really care which one it is, right? Then I know that the goal is G0. Right? So this would be, so now in partially observable environments, one design choice would be sensor placement or sensor resolution to either reduce the noise of the sensor or to increase the observation or observability of the environment. Right? Then where to place a sensor, that's a design question. And so we did this, and on a preliminary set of experiments, smaller set of domains. So on the left hand, so this is for WCD now only, no ECD. Left hand side is for action removal, the traditional action removal that Sarah talked about. Here is sensor placements, right? And I forgot, I think it's probably just removing one action and placing one sensor. Again, x-axis is percentage of reduction. In our settings, you see, in the case where things are partially observable, removing actions doesn't really help. Because if actions were removed, I still do not know which state you are, and that's the reason why I have a high WCD, right? But placing sensors, that helped a lot more. But we only did experiments where we put them in isolation, right? Something that could be interesting is that after we place the sensors, now that we could tell more things for sure, can I remove actions to further reduce the WCD? Right? So combinations of these two things are things that we will need to do in the future. Right? Yes?
On some of your charts, you had small circles without the insides. There were blanks.
Right, over here?
No, back up one. Yeah, bottom two.
Right. So these are you can imagine that these are states as well, but they are not reachable states if the agent take the optimal actions. So you can imagine that, let's say, if the agent's if the agent's goal was up here, he would have taken. I think if I have some slides that might better, yeah. So same thing, smaller, right? Without states. So this says that if my goal is G0, I would only take these red actions. I would never take these black actions down here. And because I don't take these black actions, I will never get to S1 or G1 or these other two states. If my starting state was here, there was no way I could have reached these states, right? Similarly for G1, this would be the optimal action, right? I would never reach these top states, nor will I reach these two states down here. So these states are states where they are not reachable, regardless of whatever your goal is. And then the grayed out actions are actions that you would never take. But they are there because the MDP problem or the MDP model included these states. But I just grade them out so that we focus only on the bigger states. So the WCD analysis and all that on the construction of augmented MDPs will never consider these states. Any other questions? Sarah, you had a question? You had to raise your hand earlier? No, all good? Okay. Okay.
So again, we did. Oh, you're not done.
I think I'm done. Yeah, the next is.
I mean, we did, as I said, we were planning for 3 hours. And, only this morning realized that they changed the schedule to 4 hours. So, I mean, we could stop now and then.
Yeah, coffee. Yeah, because the next stuff is going to be longer than potentially 20 minutes, right? Or you could go play the game that Sarah, our student, made.
Well, that anyway you can do during the break. Yeah, I'll have the computer here. You can play the GRD game. The idea is that you have to catch the mice that are aiming for the cheese, as opposed to the mice that are aiming for the hole. And the idea is to show you how design can actually facilitate the recognition. So you're actually trying to do online recognition and see how hard it is. And when we're going to come back, I will show you some examples, because we do have time for more examples. So we're going to show you more
applications
where GRD can be relevant, then GRD for partially informed agents, and why that is challenging and why I think that's interesting. And then we will conclude. So we'll definitely not go all the way through to lunch.
We'll still, yeah. As promised, we'll still have an early lunch break. All right. So there's no questions. I guess we can go grab coffee, assuming it's set up. If not, we'll be the first in line.
So as promised, we are going to finish early, allowing you a lot of time for lunch and maybe enjoying the other workshops that are going on. Because of, I wanted to take advantage of the fact that we have this time to go back to the example, make sure that it was clear, and kind of review review this example via the concepts that William and I have discussed, and show you an extra example, just to make sure we all understand that this framework is generic and is meant to support different planning models. And then I'm going to discuss a recent extension of GRD to partially informed agents. So how do we account for the fact that agents may not be perfectly informed? So going back to this example, what we have are agents. So just as to recall what we have here is a goal recognition setting where we have agents that are assumed to be planning agents. Now, these agents are, again, we have a model of how they behave. This model can be acquired via data, etc., etc. But it really doesn't matter. The point is that we have a model of how agents behave, and we're trying to see what it is about the environments that hinders recognition. And in this, as a first stage, we wanted to assign a value to this. So we have a worst-case distinctiveness. So in this case, it's the behavior of going up that doesn't reveal the goal. We have a non-optimal way to achieve design, to perform design, which corresponds to changes that are not necessarily applicable, acceptable, maintain usability. And this is a point that William made, and I don't think I stressed enough. The idea is to create change, but under some constraints. So in this example, the constraints are that, or in our work so far, we wanted to make sure that the agent doesn't incur a cost for the design, right? Because we can just make sure that one goal is not unaccessible, and WCD is 0, because you can't achieve any other goal. But the idea here is to maintain usability while performing design. So, and the second objective, as a secondary objective, we want to minimize the change that we introduce. So we want to minimize WCD, that's our primary objective, but we want to do that while paying the least for change, right? Because we are assuming design is costly, we don't want to do redundant design. This is where this fountain comes into play, where you walk into an airport and you are directed to your goal. Your behavior is induced, not enforced. If you guys do you guys know the nudge, the work on the nudge by Sunstein? And so they came up, I forgot the second name, sorry for that. So the idea here is to induce behaviors, to preserve the agent's ability to choose how it wants to behave. And here we are doing this by making sure that the cost is not increased. Okay, what happens if the agents are suboptimal, right? What would happen if we can't assume optimality? Then this fountain won't be enough, right? So we would have to build a larger barrier. But at some point, even think of yourselves in an airport, at some point there is some distance that you wouldn't want to cover just that is redundantly. So, right? So we would maybe need to increase the size of the barrier, but there is sometimes and often a way to create change that not necessarily doesn't necessarily affect usability. Another point that I recently realized is that here we're blocking actions, right? Or we are constraining behaviors. But recently I realized that maybe instead of a fountain, all you need is like just a little piece of grass or something that you don't want to step on, right? Maybe it's much cheaper than building a fountain, is just putting some flowers. People can step on them. It's not a hard constraint, but it encourages them to create a behavior that's more easy to recognize. As a second example, and again, the purpose here is to make sure that we leave the world of that easy grid navigation setting and kind of think of different settings. Think of a logistic setting, where we have, and this goes back to your question about partial observability. William talked about it a lot, but also in the deterministic models, we cover this. So think of this as a logistic problem, where we have, hopefully you know this very standard IPC domain, where we have a truck or multiple trucks. In this case, we only have one, and we have packages that need to move between locations. In this case, we have 3 locations. We have 3 boxes, object 1, object 2, and object 3. Sorry? What am I doing? Sorry for that.
No idea. Someone else
And
trying to be me.
yeah. So basically, we are, and in such a case, we want to understand what agents are trying to achieve. Now, please note, I come from Israel. I was very much trying to avoid security-related domains, but it was very hard in this case. as I said, now I'm working on applications that hopefully will map to other than security domains, but this is again a security domain. Think of the fact that you want to understand there are two possible goals here. So there is goal one, which is the red goal, which is the bad goal, where agents, which is the truck, represented by this truck, the agent is trying to move box 1 to location 2, box 3 to location 3, and box 2 to location 3. And there is another goal, which is the green goal, which is the OK goal, which moves the block 1 to package 1 to location 3 and package 3 to location 1. Now this, I hopefully not as clear, as obvious to you guys to understand what's happening here, because then GRD would be redundant. But what we do realize is that in terms of recognition, in terms of our worst case distinctiveness, the problem is that a block, the first block, has to be picked up anyway, right? So we can't do much about that unless we can introduce some constraints. But But in this setting, we are just the observer. This is a logistic setting which we cannot directly influence the behavior like we did in the robot. Block 1, when package 1 is picked up, there is no information that we gain. Okay, so WCD in this case is 1. All right, so this is the common prefix between behaviors to different goals. What happens if now we have partial observability? Well, now instead of packages being scattered around, now we have a shed and a docking zone where we only see the movements of the trucks. We know the initial distribution of the boxes, it's indicated here, but we can't see what exactly is being loaded and unloaded. Again, this is an intelligence example, so we are just observing the behavior, the movements of the trucks. What can we do in this case? We can actually add, and again, we can add sensors, right? So what would be the perfect place to put the sensor? We have one sensor, very costly sensor. We can put it on one of the boxes. What box would we put it on? Putting it on O1 will be useless. Putting it on O3 would be too late. The idea, the thing to notice here is that without the sensor, the truck could achieve its goal, the bad goal, without us being able to use it. So WCD here is 8. Sorry, I forgot to mention this before we talk about design. So first thing to note is that the goal can be achieved without us knowing it. Then the second question is, how do we introduce change? If we put the sensor on O2, then we guarantee that we are back to we are basically with one sensor, we're creating a situation where we have the same WCD as the fully observable case. Okay, that's the idea here. We can't do better than this in this case, in this example. If we can introduce constraints, that's great, but if we can't, the GRD framework gives us the indication of where this change will be most effective and where it would be redundant. Okay, so that was just to give you an idea of the kind of applications that we have in mind. And now I want to talk about a recent work, something that was much on my mind during my PhD. You know how PhD evolves; they kind of the things happen one after the other without having a chance to actually take a minute to kind of to take a bird's view of what you're doing. And like the point where I transitioned to my postdoc was a point for me to ask actually, what is it that I'm trying to achieve here? Why am I working on this? And I actually want to apply these techniques to real world applications essentially. And as I said, I'm very fascinated on interactions and specifically human-robot interactions. And one thing that came to my mind is the fact that, well, you can't think of supporting real-world applications without taking into account the fact that agents may be partially informed. Now, it is important to know that even by supporting the case where agents are optimal, our analysis is valuable because it gives us a worst-case analysis, right? An agent can never do better than an optimal agent, and if you reduce WCD for the optimal case, then you can then you can provide guarantees for any suboptimal case. But here I was specifically interested in understanding how to account for agents that are not perfectly informed, right? They walk into a supermarket, they don't know where the milk is. How, and I want to understand their behavior, I need to account for that model. So there are many ways to do that, but I decided to start, so I'm actually this afternoon I'm presenting a model that accounts for agents with partial observability, but in using contingent planning. And I want to give you this example as a motivating example, and I really would appreciate feedback because this is, as I said, work in progress. So now we are looking at the Wumpus example. Does anybody know the Wumpus? Does anybody not know the Wumpus? I thought like everybody in AI knew, but I get a lot of people that don't know the Wumpus example. So actually the guy that formulated here formulated this example is sitting in this building. So this is from the classical AI book by Russell L. Norvig, which I adopted. So I'll explain it. And so we have a grid world where we have an agent that starts at the initial state here. This is the start state, and it needs to and the agent is trying to achieve a goal. Okay, so it's in our case, because we are doing a goal recognition, we don't have one goal, but we have two goals, right? The agent is either trying to achieve G1 or G2. So far, very similar to what we see in GRD. The difference here is that the agent is partially informed. So the agent has a map, it knows the grid, but it doesn't know where dangers are. Dangers here are in the form of either pits or Wumpuses. Now, the agent doesn't know where they are initially, but it has sensing. So it senses the pits when it's an adjacent cell. So here it would sense the pit by sensing a breeze. When it senses a breeze, it knows that in one of the adjacent cells, there is a pit. Similarly, when there is a Wumpus, it senses a stench. So it knows that at least in one of the cells around it, there is a Wumpus, but there may be many, it doesn't know. It's a binary indication whether there is a stench or not, whether there is a breeze or not. Okay? So the idea here is to there are many ways to account for agents with partial knowledge. They cannot assume to be optimal, right? They don't know. They cannot follow they cannot necessarily follow an optimal plan to their goal because they can't really compute an optimal plan because they have partial information. So a common approach is to use what we call optimistic planning under uncertainty. So basically, what we can do is follow. So what the agent does in this case is follows a minimal cost plan to its goal, and makes assumptions about variables that it doesn't know the value of. Right. So if in this case an agent to G1 would plan this trajectory going up, right, assuming that there is no pits or Wumpuses on this path. Similarly, an agent to G2 can plan a path to its goal. I'll show the examples soon. The idea is, another thing to note is that their agents are conservative while acting. Okay, so they plan optimistically, but they are conservative. They don't take actions that they don't know the outcomes of. It's not a probabilistic model. It's a non-deterministic model in the sense that the agent plans optimistically, but it will not act unless it knows for sure what the outcome is. If it wouldn't choose an action that kills it, for example, right? Or I did not mention that encountering a Wumpus and a pit kills the agent, so that's failure. Now we introduced a specific variant to this model where, again, for the simplicity of the discussion, let's assume that the agent has access to an optimal planner. So it can actually compute the optimal plan to its goal while making as few assumptions as possible. So we are assuming that if there are two ways to achieve a goal and one requires making less assumptions, the agent will choose that path. So what's the problem here in terms of recognition? Again, the overleaf is failing again. Guys, make sure that when you use overleaf, be very, very careful because there is There is an illustration here that's missing, but basically the idea here the point here that I wanted to make is that in order to achieve G1, the agent, under the assumptions that we made, what would be possible behaviors for an agent to G1? Yes. This is risky, I know. I know asking you questions at this point is risky, but I really want the interaction. Yeah?
Just go up the left side.
Right, so you go up, right? But what about G2? What's the...
Click right click.
The what? Okay, so you go, but the G2, what will it go? Will it go this? What's the?
Up and right.
Right. So the one way is to go up and right, and another option. Right and up, and again, I mean, so basically the problem here, and thank you for participating. The problem here is that going up is non-distinctive. Right? If the agent goes right, I know that it's aiming for G2. An agent to G1 has no incentive to go right because it's planning optimally, it doesn't know better. But an agent that's going to G2, it can go both up and right. Okay? So, and again, the reason why I chose this grid is to show that this is an example where actually going up doesn't make sense for G2, but it doesn't know that. Okay? So both agents can go up, right? That's WCD is at least 1. Both agents go up again. What happens here? The agent would, both, when I say both, remember it's one agent, right? But two possible behaviors, right? So what happens here? The agent senses a breeze. It doesn't know where the breeze comes from. It may come from this cell or this cell. It doesn't know. So it backtracks. Then it goes right. And here, it stops. Why does it stop? Why now here the agent senses a breeze and a stench. Why does it and stops? Why does it stop? This is a subtle point. Yeah.
It's short and it's not at the left, but I don't know why it
doesn't go down. Okay. So first, before I explain that, let's the fact that it terminates means that in our case the WCD is 4, right? Why does it stop? It stops because now it senses a stench here, and there was no stench at the starting point. It means that there is no stench, there is no wumpus here. So it knows that there is a wumpus here, meaning that it knows that at 3.1 it will sense a stench. And it will not be able to guarantee that this cell is without a wumpus. Okay, so it stops here, but it's just a subtle point that has to do with this is a model that was created by Bonnet and Geffner in their paper of 2013, and I think it's a very subtle point, and it brings out the point. It emphasizes the point that you actually need to make sure that you understand how agents make decisions, and you have to account for that here. But for our purposes, what is important here is that worst case distinctiveness is 4. Now, how do we introduce change? So William and I have talked about introducing change via eliminating actions. We can introduce change by constraining behaviors. We can add sensors to the observer, but the observer here, we are the observer, we have full information, so adding sensors for us for the observer is useless. We could also maybe think of different ways to introduce change, but in this case, an effective way to introduce change will be by affecting the information that the agent has. So what is the model here? The model here is of an actor that is partially informed. It modeled, as I said, as a contingent planner using Bonnet and Geffner's model. And information is modeled as sensors. So now, the way we are assuming that the way the agent, the actor, collects the information is via sensors. In this case, the pairs of conditions under which pairs C and L, which means the condition C under which the true value of L is revealed, right? When I go to a cell, when I'm at a cell, I know whether there is a stench there or not. I'll give an example of that.
What we are assuming for now about the recognizer is that the recognizer has perfect information and can selectively reveal which information to share with the actor. And I'll talk about that more because that's a subtle point. But we can basically implement this as adding sensors to the actor's model. So let's see what that means and how we do this. So we call this problem information shaping. This is a this is a term that my advisor David Parks, which works a lot on game theory, came up with, and I really like information shaping as a way to induce behavior. So we select which information we want to reveal to the agent. So we can do this in both ways. So think of this agent that is entering the system. We can directly tell it, for example, by setting C to true and L to safe to 2, we can say cell 2 is safe. Okay? Indirect communication can basically add sensors to the agent, right? If this is a robot, I can just enhance its sensors. For example, in this example, this translates into being able to sense a stench at sense the stench at cell 2 when you're at 1-2. Okay, so if you're previously could sense a stench only when you're adjacent to a pit, now you can actually sense a stench when you're a bit further away. Okay, is that clear? Is that point clear? Hopefully. So let's see how that's translated and why this is tricky and why I'm working on this so hard, because the information shaping is, I think, very interesting but very challenging, and let's see why. Let's say that I decided to reveal that safe 3-1 is safe. Now I tell the agent, I have a way to communicate it with the agent directly, and I reveal that cell 3-1 is safe. That, hopefully, according to what this makes sense to you, this creates a distinction between agent going to G1 and G2. Why? Because now we gave an incentive, or in our terms, we broke ties between the plans, making the plan of going right and then up more attractive, because now the agent has to make less assumptions about this path. It's still not enough for G1 to divert from its optimal behavior, because there is still an optimal plan that the G1 thinks is better. Okay, so this is a perfect change, a perfect way to apply change, because with one change we reduce WCD from 4 to 0. Perfect. Now the tricky part comes when we try adding information, or we now tell the agent, in addition to the fact that 3-1 is safe, also 1-3 is safe. What happens here? We're back to where we were. This is a non-monotonic situation, as opposed to the models that William and I have shown, where removing more actions while making sure that goals are achievable never increased WCD. Here WCD can actually increase, which means that all the techniques that we used previously don't apply, and we need to apply information shaping we have to be very careful on the way we apply information shaping. So again, what we do here is apply a search. We wanted to search for design solutions that minimizes the worst case distinctiveness. We want to do it in a way that kind of makes sure that we don't exhaustively explore the state space of design options, because even in this very small example, just think of if we have a budget of 3, I mean, this is always already just selecting 3 out of these 25 is already very exhaustive. It takes a very long time. So how do we do this? And this is, again, as I said, still work in progress, but what we need to account for here is that, first, the fact that information shaping is non-monotonic. We need to account for that when we perform our search. Or basically the way we reduce our search space needs to account for that. We cannot explore the state space exhaustively, and the approaches that William and I have showed for the deterministic cases or the stochastic cases where agents are perfectly informed don't apply here. We need new techniques. And the techniques that we came up with have to do with, we like to think of ways to automatically extract information that is irrelevant for the GRD case. What we did here is, so we decided to use techniques from classical planning. So what we did first, as a first stage, we compiled the agent contingent planning problem into its corresponding knowledge compilation at the knowledge level. So Bonnet and Geffner have a compilation that compiles the classical planning, the partially informed problem to a classical planning problem. Then we extracted the causal graph of that problem. So the causal graph is an entity that reveals relevant information from the problem. What would constitute as relevant objects and relevant information, and that allowed us to do safe pruning. So whatever information does not appear in the causal graph of any of the goals can be safely pruned. So I don't want to go into the details. This is not, I don't think this is the place to do that, but the idea is that the point that we wanted to make here is that classical planning tools can be used for GRD and not only for modeling the agents. We can compile the problem and use classical planning to find the worst case distinctiveness, but we can also go beyond that. And we can use causal graphs, which are commonly used in planning here, in order to extract what is relevant information. So for each problem, for each goal, we create a causal graph, and this causal graph reveals which information would affect the agent's behavior, right? So, for example, if we extend the problem that I showed you to a setting where for the agent actually needs to collect the key on its way to the goal, using a causal graph reveals what objects are necessary for the agent to reveal the goal. And for example, if there is an agent that's aiming at G1 and there are 3 keys distributed, I know that telling the agent anything about key 2 or key 3 is irrelevant in this case. So automatically understanding what information is valuable. In terms of applications, as I said, there are many applications where goal recognition is relevant too, but design can actually be applied. So, for example, assistive cognition is where agents are maybe need assistance from a robot, and there is a way to actually design the environment in order to support this type of collaboration. Intrusion detection, the same example that I showed you before, but now we cannot no longer assume that agents are perfectly informed. There is collaboration in general, human, factory lines, etc. What I am trying to do now is to actually implement this technique to a navigating robot example. So the robot has a map, occupancy grid of the environment, and I can directly communicate with the robot. It's a robot that I can't change, but what I can do is I can affect the map. I can change the map, the occupancy grid, if you guys know what that means, but basically the map that the agent used to navigate. I can manipulate that in a way that guarantees early recognition. That's it. We wanted to do the conclusions together, or you?
You can start.
Okay, so to conclude, and again, we were planning for 3 hours, so you have a very long break or a chance to see the other tutorials. What we covered today is work that we've been doing since 2014 on various forms of GRD where agents are planning agents, but that's not the only work. Since GRD was formulated, there is also work on plan recognition design where they're using plan libraries to model agent behavior rather than planning domains, rather than domain theory. There is a work by Masters and Sardina where deceptive path planning is used to understand how to account for agents that are actually trying to conceive their goal, right? As I said, the work in 2015 also accounted for agents that were trying to deceive the system, But here in deceptive path planning, they are using a probabilistic model, so they generalize that. And there is also work on game theoretic goal recognition models where the agents are actually in some types of, William can say more about that. There is so much I can say. So in terms of conclusion, what we showed you is goal recognition design as a way to perform offline design for efficient online recognition. Hopefully I managed to convince you that there are a variety of applications to which this is relevant, and if you want to see the code and benchmarks that I've used for my work, they are all here in my GitHub repo. And you wanted to talk about the challenges?
Yeah, well actually before I want to also talk over here, I think Merske et al. They also have a JAR paper now that has a more larger description of their work. And Masters Sardina, I think they had an AMAS paper this year extending the deceptive path planning work that is pretty exciting over there as well. So essentially there are things that say, what are the probabilities of the goals of the agent in the worst case, even if the agent is trying to deceive you of where it's trying to get to, right? So if you're interested in those kinds of problems, then this is definitely something to read about. The goal recognition setting here, this was where it's kind of like an online game now. You have the agent and the recognizer, the observer. The agent is trying to get to a particular goal. And imagine this is a terrorist application. If he gets to the goal, he gets to bomb the airport. You need to figure out which terminal they want to bomb. And then the defender or the observer can then shore up defense or resources at the different terminals, but they only have a limited amount of resources to shore up. So if I guess as a defender, if I guess your goal wrongly and I shore up the wrong terminal, then really bad things happen, right? So that's essentially work over here that together with Albert Jiang at Trinity and his students, this is very, very preliminary work. So a lot of things that could be done over there to improve it. And open challenges, I guess, one thing that you can easily see from this table is that it would be ideally there's a line somewhere that has a check mark for everything, right? And obviously that's not there yet. And a lot of our work, I guess, we have extended the default model up here in orthogonal directions, right? Yes, suboptimality here, partial observability there, partial observability from the environment's perspective, from the agent's perspective, but no unified model that could do all of that yet. And that's the reason for that. It's challenging, but that needs to be done, right? So that's one of the challenges I think that if you guys are interested in, there's a lot of room for work. Another thought, I guess, that almost all of this work over here assumes that the agent doesn't really care that its actions are revealing information, right? I forgot what the three terms, three types of agents.
Agnostic, adversarial.
Right.
Yeah.
That we're only assuming that it's agnostic setting. The only adversarial setting, I guess, is stuff down here. But goal recognition, I mean, it's especially in security settings, adversarial settings make sense, right? It doesn't make sense that the agent is going to act optimally, right? So there's how do we extend stuff like this into this adversarial setting? That's also an open challenge. And the other things, right? So far, Sarah and I, we've been talking about things like WCD, ECD, and so on. These are all just offline metrics because it's an offline problem. But the actual reason why we're doing GRD is to improve goal recognition. And I guess in the last 5 years at least, no one yet has done the work. All right, if you really do this design, do you really improve goal recognition? Right? Right? With existing goal recognition algorithms for which there are tons of, right? Or yes, maybe you reduce WCD, but goal recognition is still a really hard problem, right? We have no idea. So there's that disconnect over there as well. That, I mean, we could work on it, but we hope more people work on it, right? And then stuff like the usual thing with all these kinds of work, with domain independent work, mapping deployment to real world applications. That obviously is, at least for me, it's a huge goal, right? We're doing this work so that we can actually impact lives, right? But on its own, goal recognition and goal recognition design is probably won't be able to do this, because things like we assume that, we have the model of the agent or the model of observer. Most of the times the agent might be a human, right? How realistic it is for us to actually have a model, an accurate planning model of the human, right? That's probably not going to be very realistic. We can maybe approximate that, but then how do we approximate that? We need to use reinforcement learning techniques and so on. So combining stuff like GRD with stuff from reinforcement learning, or even with stuff like explainability, right? That's also linking to the other areas that are sister areas to GRD. That's also going to be interesting, right? Especially as we want to deploy stuff to real-world applications. And there are tons more. So I guess we're also hoping to hear from you guys on, what you think are things that we should work on, that the community should work on, or if there are any open questions that you guys want to ask. Any thoughts, last minute thoughts, final thoughts? Yes, Ben.
Kind of final thought, but the slides, especially since coffee break, are different from the ones on the website.
We will update the ones over there with the latest slides over here. Yeah.
Yeah, sorry.
So
they're the same, they're just reorganized, but I'll...
Yeah, so yeah, there's some new stuff with the examples and I think
oh, sorry for that. Yeah. Sorry.
Mm-hmm.
Yeah.
So we will update the slides over there with the latest ones, and hopefully maybe after the animations get updated too.
Yeah. We'll update the correct. Yeah.
This is the result of cloud-based collaborations and syncing and so on.
I have a question. I have a thought.
Comment. Yeah.
So you guys worked on stuff and you assume that the agent is optimal right now. Now, in an environment where you're doing human-robot collaboration, say, you'll have multiple humans maybe solving the same task over time in some different kinds of ways. So is there any thought given to how you can combine these different kind of traces that you have gotten over time and sort of build a model that works well in the worst case or the average case, something like that?
Right, so I guess that goes a little bit into the RL perspective, right? You have all these traces, can you use the traces to essentially approximate the model of the human and so on. I know I haven't worked on that, so I'm not sure.
The point to be made here is that we could account for different models, right? Not necessarily one type of agent. And then the question is that's actually, well, we started thinking about it in the context of interoperability, but there is the question then is what are you trying to achieve? If it's still a worst case analysis, then combining the model is a great concept. So you have to, this is still work in progress, but the idea here would be to combine different models and actually figure out what would be a design that would enhance all models. Yeah. I think so. That's a good point. Yeah, not yet done, but a very important point.
And I guess if you do the approximation route, then you have to also consider that worst case over here might no longer be the actual worst case anymore, right? There's approximation errors and all that.
Yeah.
So that needs to be taken into account. And then when you're talking about multiple users and so on, something that Cristobal and I have been thinking about as well is all the work over here assumes that there's only one agent acting. Right? What if you want to observe the goals of a team of agents? Right? Maybe 3 guys need to go over there and 2 guys come over here, and then bad things happen. Right? So now how do we extend it into this multi-agent recognition perspective? The trivial way would be to compile all these multiple agents into a single big agent, right? With the state space of 3 to 5 different agents, for example. But there might be better ways to do that. Right? There's something another possible extensions. Right? Yeah, thoughts?
Yes. Well, this can be also offline if you guys have questions or thoughts during ICAPS.
And you have our email addresses. Feel free to email us or catch us whenever. We're happy to talk about this. Or better, catch my student. Because that's all. She knows this work so much better than I do. And also like to thank her. I guess a lot of my images and so on are stolen from her slides. So she's the original author of it. All right, in that case, well, thank you all for coming, especially from 8 a.m. this morning.
Yeah.
Have an early lunch break. I'll see you guys later.
Enjoy.